Hi everyone. Thanks for having me here. It's a real pleasure to be presenting some of the recent work to all of you. So I can introduce myself with the topic for today. It's quite a mouthful here, but hopefully over the next 50 minutes which we have, I should be able to explain at least some concepts from this to you. I've linked the paper, and let me get my pointer out over here. So I'll be pointing at many things during the presentation. So if you actually want to see the full technical article, then feel free to look at this link. I'll share this after the presentation as well. I can maybe start off by introducing myself. So I'm my day job is I'm a research engineer here at Google DeepMind, based in the San Francisco Bay Area. I specifically work in its applied group, which is quite exciting. Our group specializes in taking the best of what we see in our company's research and finding opportunities in which we can apply this to our partner teams. So you might have seen some of the recent work we've done with YouTube, with Google Play, etc. So that's our group over here that tries to figure out how we can achieve impact more broadly. Prior to DeepMind, I joined DeepMind in January 2020, so just before the pandemic struck. So quite an interesting time for the world and for me, joining a new place. Before this, I was at Google Cloud. I worked as a machine learning cloud engineer, was the official title. But basically what that entailed was working with some of cloud's biggest customers and figuring out ways in which we could create lift for them or optimize some of their workloads using our machine learning research tools. An example of that would be we figured out a way in which we could learn something called a contextual bandit. It's a type of machine learning or reinforcement learning technique where we could provide more accurate recommendations to users by meta learning this, or teaching an AI how to learn. It was fun. 1.5 years at Cloud before I moved over to DeepMind. And prior to that, I was in grad school in Pittsburgh, Pennsylvania. So I moved to the Bay Area for work, and I've been here for roughly 4.5 years. Okay. So today we will be talking about, as I said, talking about how broadly we developed simulations for industrial systems. But the question you might ask is, why do we care about this? Why is this important? And the broader goal of what we're doing here is to help in the existing research, which is ongoing, on how to make these sort of systems more efficient using these artificial intelligence techniques. So I'll first be covering, motivating the problem and telling you why this is an area of active interest globally. Then I'll deep dive a bit into what a simulation looks like. Hopefully it shouldn't be too technically heavy for all of you, so I'm trying to skim and stay at the highest level, but if it is, just let me know. I'll just skim through and then we can look at fun GIFs I've generated or some of the cool results we have using reinforcement learning agents to play on these simulated environments. And then I know there might be other broader questions on this presentation or other work I've done or any Q&A. So I'll leave some, maybe at least 10 minutes towards the end for any questions which all of you might have for me. But also feel free to interrupt me midway, if I'm speaking too fast or something's not clear. I'm happy to take questions in between. Cool. So with that, let's start by introducing the problem. So this is a pretty nice plot over here. This is still 2016. I borrowed this from a previous slide deck, but I think we can all extrapolate and understand what's going on here. So you're seeing this increase in global temperature over the last few centuries, and most people call it one of humanity's biggest existential crisis. I won't go into too much detail, but if you're in this room, you're here, you already know what I'm talking about. So we're kind of approaching this this inflection point in global temperatures, which could cause irreversible consequences to our world, and of course a massive impact on our ecosystems and all the lives that live over here. So it's quite an important challenge for us to focus on. And there are various causes of, global temperature change. We can go through all of them, but the one we are focusing on today are industrial systems, which we have seen around us in major cities, urban areas. You might have seen structures like this. So these systems account for approximately 54% of global energy usage. I'm just quoting from a paper. You can look up the references, the official study numbers from there. And 24% of the global net anthropogenic greenhouse gas emissions. So this percentage actually rises to 34% if you also consider indirect emissions from energy. And if you put in these numbers together, it would actually make industrial systems the highest emitting sector overall. And to add on to that, due to the increasing demand, for products and services which are enabled by these industrial systems, it would be reasonable to assume that emissions from this sector will continue to rise over the next few years. So that paints, quite a bleak picture. But there have been recent approaches by many folks on how to at least think about solving these problems or mitigate them to some extent. So data centers, they generate. I have a photo here of data center, and as you can see, they generate. They're quite massive. You can see it spans quite a large corridor. They generate a lot of heat. So there's a lot of infrastructure required to also keep this within certain temperature requirements. So the cooling systems are also massive. So, for example, I'm talking to you right now. I'm streaming via my laptop, and I also have a presentation open. And even with this, I can see my laptop getting a bit hot, right? Now, imagine if I extrapolate my laptop to the size of an industrial system, it will generate a lot more heat, right? So yeah, given this, it's not really surprising that we need a massive amount of energy that's used to cool these data centers. And this is one of the largest sources of energy utilization, apart from the non-server load, of course. So as I briefly motivated, there's open papers out there. There's been a lot of works in industry and academia on applying reinforcement learning to optimize these systems. I unfortunately don't have a slide on the reinforcement learning primer, but for the purposes of today's presentation, just assume it's a form of these artificial intelligence techniques that's used to perform actions in a sequence so as to optimize for an objective. That's also quite a mouthful, so let's just think of it as a black box artificial intelligence model, but I'm happy to answer questions towards the end. But basically, there's been a lot of research in this area to find good control mechanics so that they can find out ways in which you could maybe make the cooling more efficient by using lesser energy, right? The challenge with this, though, is like most of the work done is with direct interactions with these industrial facilities. So when for training agents, you usually need data, right? The agents look at data, create mental maps. Think of it as mental maps of how to act given these data streams, and then it learns from those, and then learns a hopefully reasonable way of acting in the real world. So the challenge with this is that when you work with these real world facilities, there is limited exploration. As you can imagine, you have to make sure the agent doesn't do something really crazy so as to cause drastic action. It has to respect a lot of constraints and keeps things within bounds. So in typical academic literature, we call some of these challenges exploration, generalization, learning, sample efficiency. All of these are various issues that plug this area of experimentation in real world facilities. So that kind of motivates the need for a simulation test bed such that it can allow researchers a bit more flexibility in the kind of hypothesis which they want to test out without directly putting that in a large scale environment and then something drastic happening. Any questions so far, though, if I continue further?
None here.
Okay, cool. So that kind of motivates, creating an industrial test bed. So you can have researchers play around with their agents in these simulated sort of environments. There has been prior work in the field. For example, what this GIF you see is the industrial control suite. It's introduced by DeepMind, and it's mostly for robotic manipulation tasks. So you can see like agents grasping certain things, trying to like balance a stick, trying to walk. Mostly in the manipulation, and you can think of maybe the humanoid domain, but of course it could be extended. So we decided, our group at DeepMind, to kind of extend on this for industrial systems specifically. Can we develop a simulation suite which could then be used which supports a backend of these industrial system simulations, such that we can use this as a test bed for these artificial intelligence agents where it can learn from these interactions with the simulations, with the goal that probably in the future it can work well in real world environments. But the real world is quite complex. There's a lot of things going on there that makes it quite hard to quantify and build up a simulation. People move around. For example, you're currently in a building, you're at home. So let's say you're going into work, you're usually there from 9 to 5, and most people are in from 9 to 5. So you think of like the amount of cooling requirements in buildings on, let's say, a hot summer day. You can think of a spike when people come in the morning and kind of tapers down when they leave in the evening. But the other factors too, like weather. It's usually warm in the midday, so that also, given the same number of people in a building, usually you would need to cool it more, let's say at around 12 in the afternoon versus 8 p.m. in the evening, right? So there are weather patterns, both daily as well as seasonal, that need to be taken into consideration while designing these simulations. So we need to account for I call these more broadly scenarios. So we need to account for these scenarios as well. So given all this, we decided to create something called the Industrial Task Suite. What you see here is a bunch of really large, really confusing block diagrams, but this basically just motivates the architecture of what we build on a very high level. So we have, we build simulations, which I'll explain in the next few slides, but we build all this other stuff you see here: environments, constraints, noise, scenarios, as a way of interacting with the simulation and being able to train a reinforcement learning agent to learn from these real world setups. So for example, if I want to train an agent to, let's say, control the building, a random building in summertime in California, right? I can set up my task suite in a way that it takes in these environment parameters and the building parameters and creates this simulation so that the agent can interact with that, versus a building in, I don't know, like Scandinavia in the winter months, right? I'm not sure it will require a lot of cooling, but it'd be interesting to simulate that too. So I guess I can just gloss over this for now. It's not really meant for the audience here, but if you're curious about how we set this modular block diagram up, I'm happy to answer questions later on. So I can talk a bit about what, on a very high level, what a chiller plant looks like. And this, what you see open in front of you right here, this is basically representative of what you would see in most buildings around the world. So you might not see this walking into the building, but behind the scenes, in the basement, on the rooftop, the same mechanics, the same thermodynamic properties applies everywhere, and this is how your building is kept cool. So very broadly, there are two halves to the system. You have the condenser water side on the left side, and then you have the chilled water side on the right. The chilled water, let's start with what's on the right side, right? So the chilled water side, that's what sits closer to us. That's what interacts with us humans in the building. So if you look at your roof, or if you're in an office, or you have central air conditioning, you'll see these vents in your room. And this is basically how the system's able to suck up, like the hot air generated by us, and then provide cool air based on the thermostat which we set in the rooms. Let me get my pointer out for this. So if you think of this as, you as occupants in a building and there are multiple floors. So let's say you're generating heat. The cold the cold air comes in, it cools the room, it absorbs your heat, and then this heat comes out of the building and goes across to the central section called hex and a chiller, which I'll explain in a bit. And then these two magical items, it cools we are now talking about fluids. It now cools the fluid down over here, and then the fluid goes back to the building. So these two brightly colored loops, the red loop over here and the blue loop over here, these are basically water loops. And we'll be talking about water-cooled chilled water plant systems for cooling buildings.
Could I ask you a quick question?
Yeah, sure.
So just for clarification, whenever I saw this paper initially, I thought it was like specifically for like industrial like factories almost. But you're saying this applies to like any building that has AC?
Yeah, most buildings, yeah. I mean, if you go to your roof, you'll see like these structures, like these circular discs, and they're rotating and all. That's basically something called a cooling tower.
Got it.
Right? Most buildings have this, and I think it's a basic fundamental property by which they operate on.
Yeah.
There might be new advanced machinery, but I think almost every building has the same sort of setup. I mean, they might have like I'll talk about this in my exact next slide, but they might have like 3 chillers versus 1 chiller, multiple pumps, but these basic components they all hold.
Got it. Thank you so much.
Yeah. Cool. And then on the left-hand side over here, you have the condenser side. So yes, as Lindsay said, you have this applies in regular buildings as well. So you have cooling towers, and this is typically kept in the rooftop to directly interact with the air. So basically, think of it as water on this side of the loop is used to cool water on this side. So basically, it absorbs the heat from here, and it gets slightly warmer, and it goes to the cooling tower. The cooling tower, at the cooling tower, the water then gets evaporated, and by a thermodynamic process called latent heat evaporation, it then releases this energy, which is then used to cool the water by the interaction with the air blowing through the. So air blows to the cooling tower through a fan, and that's used to then cool the water. And now this cooler water then returns back to this central hex chiller area, and then the cycle repeats where cold water comes in here, absorbs heat from here, and then goes back here. And on this loop, same thing. Warm water comes in here, it gets cooled down, goes to the building, absorbs our heat, and this entire cycle continues. The discrete components here, so you can see there's the building load. So think of it as us occupants in the building. You have a chiller. This is a device. The way I like to explain it into a single line is, it's a piece of machinery that's able to make a colder medium cooler and dump that in a warmer medium. What do I mean by that? Let's take a specific example. Let's say water is coming, from the building. It's coming in here at the United States. We use Fahrenheit. So let's say it's coming in at like 55 degrees Fahrenheit, right? Like the water's pretty hot. It's 55 degrees Fahrenheit. The chiller is able to cool this down to, let's say, 45 degrees Fahrenheit, right? A 10 degrees drop. So there's a 10 degrees decrease in temperature, and that consumes energy. So where's this temperature, delta thrown out at? And it's done over here on the chilled water side. The condenser water side, right? And the beauty of this is the chiller can also, up to certain physical limits, of course, but the chiller can also work if, let's say, the temperature, it's a hot day outside and it's 60 degrees Fahrenheit. If this temperature here is 60, and this is already colder at around 55, it can still drop here. It can still dissipate its heat to another medium that's warmer than it, right? If this was 70, it could still do that. And even if it was colder, let's say it's 40 degrees, it would obviously be able to do that more easily. In which case, you wouldn't need a chiller, you would use a heat exchanger. That's a separate concept. But the central way to think about what this does is it's able to make a colder medium colder by dumping the heat into a warmer medium. Does it sort of make sense on how the chiller works?
I have a question. So when you dump cold, oh my gosh. Okay, so let's say one is 70 degrees and
Yeah.
the other one is 50 degrees, but you're trying to make the 51 45 degrees, right?
Yeah.
Would that
Yeah.
make it 75 degrees, the other one?
Yeah, that's a great question. Yes,
Okay.
it would make it 75 plus a bit more.
Okay.
And then that's a term which we account for like energy wastage. It's not a perfect process.
Okay.
So it consumes more energy for that cooling. So it would make it maybe 75 plus a 2 degrees energy wastage. So around 77.
Got it. Thank you.
Yeah, great question. Cool. And I think, the point I discussed before this was good to describe the heat exchanger. Let's say it's a very cold day outside. So let's say it's the water's at 48 degrees, right? In that case, we won't need a chiller to actively consume energy to actually do this cooling. We could simply use the heat exchanger, and the heat exchanger is, as what the name suggests, it's just like two pipes where the water does not physically cross over, but they just come very close to each other, like the metal pipes that the waters are flowing over. They just touch. So by conduction and convection, there's a temperature from the hotter to the colder and vice versa. So like they kind of neutralize towards a midpoint, right? So let's say it's a cold day outside, again like 48 degrees, and then this requirement here is from 55 to 45. The leaving temperatures at both ends, so here and here, would kind of be close to a midpoint. That would, of course, depends on other factors. Like this is simplifying assumption, since this would depend on stuff like how fast the water is flowing in one pipe versus the other. But let's assume we are keeping all that, it's all equal. We would see gradual, equalization. So this pipe here would be able to directly cool this down to a lower level. Cool. Any questions on this slide over here?
No.
Okay. So in the real world, it's more complex. I won't really get into it too much detail because this will obviously take more than an hour, a few hours. But as Lindsay said, these sort of cooling mechanics, they work in various kind of facilities. It can work in a small residential building. It can also work in a large data center industrial facility. And as you can imagine, the cooling requirement for a couple of residents is very different from a large data center, right? And so you would need different number of these chillers or cooling towers to satisfy that cooling requirements. Chillers are rated for a certain amount of, the term is tonnage. So they are rated to provide a certain amount of cooling in terms of this quantity. So if it's, let's say, a small building, you might just go with one small chiller, versus if it's a large industrial facility, you need multiple of these in parallel. So think of it like batteries, like a fully electric car, they require a lot more batteries versus, like a handheld remote, it requires obviously a smaller AAA battery, right? So different building topologies dictate different architectures, but they overall consist of these same, similar fundamental units. So I'm showing an example of something that's for something slightly more complex. So you won't have a single chiller like you do over here. Rather, you'll have three chillers in parallel where you'll have the warm water coming in from the chilled water side. It splits into multiple smaller pipes, so less amount to cool, and they go to different chillers that's able to control them, and then it gets cold water. So at same analogy, you might also have multiple cooling towers, multiple pumps, all of these defined to account for the different cooling requirements of the buildings. This diagram is a bit important because if you ignore like the multiple chillers aspect, you see that I have this this text over here, right? It says chiller leaving temperature set point. And yeah, we have a couple of others, condenser set points. We have 5 of these, right? So these are basically recommendations which the building operators, so let's say whoever designs these building management systems, they said at what temperature should I want the water to be leaving from the chiller so as to maintain a constant, let's say 72 degrees Fahrenheit in Praneet's room, right? So the building operator writes an algorithm and says, okay, if it's a warm day and if, this humidity, then set the chiller leaving temperature to this value, and then we'll meet the cooling load, right? So the building operator, they set, let's say here it says 42 degrees Fahrenheit, and it sets this recommendation. And what happens below that is this low-level implementation or recommendation. So we have these controllers that's able to figure out, this is a recommendation, this is what the current value is. I need to change something in the machinery so that the recommendation meets the current value. And that's a process called, here I show it's called a PID controller. I'm forgetting the full form I should. So I think it's proportional integral derivative controller. We don't need to get into that. Think of it as a sort of like robotic system that's able to meet the requirements with what the current value is. And these sort of set points, so you see this one over here, the chiller leaving temperature, the pressure. So basically we want to look at things like temperature, pressure, and water flow rate, right? These are what can typically be controlled. So here we're controlling the leaving temperature. Here we're controlling the pressure between 2 points. We talk in terms of differential pressure between 2 points. We can talk about the flow rate of water on the condenser side. How fast do we want the water to be moving? And then how fast do we want the cooling tower fan to be moving? So we control the temperature based on how fast the fan can move. So these are all control mechanics that before we got these artificial intelligence techniques involved were written by algorithms, and they figure out what the optimal value for these are. Any questions on this?
No.
Cool. Okay. So if we kind of formalize this a bit more, you can see here I have this table, and this is 1, 2, 3, so around eight values here. Think of these as 8 actions which somebody who's controlling the building needs to set, right? So I briefly said, you can control what the temperatures, pressures, and flow rates are, but you can also control more complex things like, let's say that nobody's in the building on a winter day, right? In that case, you don't need as much cooling. So you can say, I don't need to run 3 chillers. I can just, run a single chiller, right? So the agent or the building operator can also control this, when to switch on and off a chiller, a pump, or a cooling tower. But another point I will mention is that these systems are quite complex, big pieces of machinery. So to accurately kind of, if you keep switching them on and off, there's a huge ramp up latency. Think of like starting, and I want to say car, but that's usually instantaneous, like a large ship or a large aircraft. There's a huge ramp up time when the engine completely ramps up, right? So when you think of this large space of optimizations which you can do, like switching on and off a chiller is quite wasteful if done very frequently. And there are ways in which you can kind of meet the requirements without kind of trying to like switch them too frequently or change set points too much, because those consume energy. So I think now's a good time. I can make this bit interactive. So let me explain how reinforcement learning comes in here, or what, how does this motivate the problem I said earlier, right? The question now is, can we use reinforcement learning to, control all of, set all of these actions, set these recommendations, so that it can meet the cooling requirements? So for example, I want 72 degrees Fahrenheit in my room. So can it be able to provide me this level of cooling while minimizing power? That's basically it in a nutshell. It's a bit more complicated, so it has to meet the cooling requirements of my room, some other rooms, third room over there, and some other constraints. But basically think of it that, meet as much cooling as done without AI-based control, but now try to minimize the amount of energy required which was done before, right? This is something which we call the constraint optimization task. And a question which you might have is, why don't we just, if you don't have constraints, right? Like somebody might say, why don't we remove all the constraints? In that case, if an AI says that, oh, there's no constraints, I don't care about what temperature Praneet wants, in that case, I just turn everything off. Like I turn the chillers off, I turn the pumps off, I turn the cooling tower fans off, everything that consumes energy, I just turn these off, and then there's no cooling met, right? And like I'm using zero energy. I met my objective. I minimized power to the ultimate value. That's not really good, because then building the occupants in the building are going to complain, and it's not going to be a very good end state. So that's what makes this complex. You want to maximize the goal, which is minimize energy, but you also want to meet the various constraints across the system. And this is quite a complex problem to solve, which is why reinforcement learning techniques have become quite popular in trying to solve them.
Can I ask you a question?
Yeah, go on.
This is probably a very silly question, but just to understand what's at play here.
Yeah.
Is this dissimilar from like a nest, like something that learns?
Yeah, so I'm not sure about Nest specifically how it works, but
Okay.
I guess like the basic principle is the same. Nest kind of tries to figure out, I mean, from my limited understanding, it tries to figure out when you're in the house, what temperature you like, and tries to set those. I'm not sure if Nest tries to optimize the energy use. It just tries to optimize for your happiness metric of what temperature setting it is, right? So
Okay.
yeah, it's in a similar light. It tries to learn out relationships between what's happening in the room, how much do you adjust the value, and then try to infer that relationship to provide recommendations. In this case, we care about all of that, of course, but we also care about minimizing the amount of energy used, so
Right.
we can minimize that carbon footprint. Yeah, so that's basically it. Interest of time, I'll skip through a bit. Some of these are quite heavily technical too. But for the agent to kind of operate efficiently here, it needs to also understand the environment. So, for example, Lindsay, if you're changing the temperature to your nest, it should be able to see what those adjustments are and figure out, okay, I need to maybe keep my operating parameters within this range. So basically, in reinforcement learning literature, we call this observations. So the observations which the agent can see so that it can take actions in the environment that maximize the reward subject to these constraints. Again, that's a bit complicated, but if you think of just the definition I said before of like trying to minimize energy, but keeping the building occupants happy, that's basically what the agent does. But it needs to see certain things to do those, and there are these values over here. I might skim through the section a bit because I think we have like roughly 10 minutes left, but the TLDR is, I DeepMind, we started building this up, the simulation framework. So as you can imagine, this is quite complex. There was a lot of reading and understanding. I'm not a mechanical engineer, so there was a lot of literature surveys that need to be done to understand how these systems work together, how to design them, what would be a nice way of even linking this up with reinforcement learning frameworks. A lot of infrastructure work involved as well. So we started simple. We started like looking at these systems in isolation and then trying to link them together. So the chiller is kind of the heart of the system. That's what, I like to think most of the magic, in terms of most of the energy consumption happens in most situations. So when I say most, I mean there are caveats. There are zones in which the chiller consumes much less amount of energy and then the pumps can become quite expensive. But this is one assumption we can hold for now. So chiller is quite important to model. And we basically, so what you see here is just how this breaks down into plain physics. Different components here. You have evaporators, expansion valves, condensers, and compressors. We can focus on the compressor because this is where our control comes in. We can control the compressor. It's a device that consumes energy and then it's able to change a low temperature and pressure vapor into a high temperature pressure vapor and have this thermodynamic cycle. But basically, this is what we have control over, right? If we run the compressor higher by supplying it with more power, this double comp term here, it'll run faster and cool the building more. If we give it less power, it'll do less cooling. So that's basically it. So we were able to find open source papers that was able to give us a nice analytical closed form solution of how a chiller works. And this was really helpful since we didn't have to create a full 3D simulation, which would be quite costly and expensive to run because it's quite heavy. It would take quite a bit to run, and the learning would be quite slow. The TLDR it was something as simple as n equations and n variables, and we were able to match the chiller operating characteristics to with these simple approximations. We ran a few graphs to see how well does this work in practice, with let's say a real chiller. And we see that these equations held qualitatively to what we would expect it to be. So okay, cool, this reasonable assumption would work well for us as a baseline. We did the same thing with the cooling tower and the pump banks. We read up papers, we tried to implement them, and we see that they match really well to what we would hope to see in practice. So That's great. So we simulated all of these components in isolations. We had these semi-analytical solutions for those, which is what the name of the paper is. And then we used a commercial multi-physics solver called COMSOL to kind of join them all together and create a simulation of this. Yes, I'll now jump to like the layer above that, like how this is important, how we create a task suite. But are there any questions on the simulation design? Okay, cool. I'll move on to the task suite. So what I showed you right now, like the chiller plant, the cooling towers, the chillers, the pumps, etc. That's just the simulator, right? That's something which we created with a physics solver. But now the question remains of how we can actually use that practically for reinforcement learning training, right? There's a lot of infrastructure that goes into it. We want to make sure this is something scalable, that's something that's very easy for researchers to test out different hypotheses on and swap out different sort of characteristics. So we have to build this architecture, which is called the industrial task suite, to support various backend simulations. So for example, I'll show you a simulation of a motor and an aeroplane's airfoil in the next few slides, a nice GIF, but we can support a wide diversity of simulations over here. So there can be different simulations which researchers want to try the algorithms out on. There can be different scenarios. So for example, different weather conditions, building load profiles applied to a given simulation. And there can be different tasks. For example, let's say I care about minimizing power with respect to the, certain constraints, such as the temperature in my room. You might care about your room as well. So there may be different tasks. Somebody might care about maximizing power. So people might want to be flexible in which they want to define the task, which they want their reinforcement learning to be able to actually solve for. And then the real world is noisy. There's, sensors. They get pretty bad if you use them for a long time. There's a lot of noise in the environment, like the observations we get back from the environment as well. So we want to modulate this real world noise and disruptions as well. The TLDR is, it took us a year, and we managed to build this up. And we were able to design this task suite so that we could control for different combinations of tasks, simulations, constraints, and noise. So you can see here, a simple task would be just minimize power, right? If you just have a simulation of a chiller plant and we tell a reinforcement learning agent, can you minimize power? What's it going to do? It's going to learn to just turn all the chillers off and that's it, right? But what if we tell it to minimize all the power, but say that you need to keep at least one chiller on, right? If it turns one chiller off or it uses more than two chillers, because the bound here is use 1 to 2 chillers, we'll penalize it heavily. So in this case, the agent will learn to use a single chiller, but use it at a very low power utilization so as to respect the constraint, but also minimize power. And you can imagine this expands all the way up, all the way till, you want to minimize power. You have like 20 or 30 different constraints, and you want to control a 10-dimensional suite of actions which involve power, temperatures, pressures, flow rates, and chillers, etc. But basically, we have the task suite so that we could run different combinations of these and test out what agents do at different levels. And we have like a label for these, so we can say like, oh, what's easy for an agent to solve versus what's hard, so we can kind of like baseline what the performance is. Any questions on this?
Not now.
Okay, cool. I can skim through the slide. This is some graphs of like how we ran different agents on it. So the x-axis is like how long it took, like how many steps it took to interact with the agent, and the y-axis is think of it a reward, how much it does the task well. So higher the better. So you can see usually it starts off low and then it tapers out high. And then the different plots you see here, these are just different examples of reinforcement learning agents. So you can look at the paper for more details, but basically we were able to get good results. And finally, I'd like to end by showing you some visualizations. I think that's always nice to look at. Unfortunately, it's not from our HVAC simulation. I don't have one ready, but as I said, we support a wide diversity of simulations just beyond industrial buildings. So in this case, we have a motor over here, and basically we want an agent to control the rotation speed of the motor by controlling the amount of current. For those of you with electrical engineering background, if you like build a current, you can change the rotation speed over here, and you can see different metrics such as how well the agent's doing, what the current target and position is, and what the action the agent is taking. Okay. We also generated this for airfoil. So most of us have been on flight. So if you've seen your plane, in your airplane, there are wings, and then I'm actually getting a private pilot's license right now, so I should be able to speak of this more technically. But basically, when you pitch up or you pitch down, you can see the wing attacks the air at a different angle, right? So this is another simulation where you can see the fluid flow of the air across the wing, and then if you want to control it to hold it for a certain altitude or a certain any pattern that you want, how we can control the pitch of the aircraft so that we could hold that given scenario. So these are just nice visualizations, so you can see how agents are able to control other real-world systems apart from our industrial controls, our industrial facilities. And it's really nice to actually see all of this work. And that's all I had for today. I know I rushed through a lot, so I'm happy to stick around for questions towards the end, maybe even beyond time. But I guess we can take any questions now on any aspect of presentation or anything else.
This is Peter, are you only applying, only it'd be silly if you're Google, but what are some other fun places you're applying these things besides, like energy reduction in chillers? That you can talk about.
Yeah. So I'm not sure. As you said, Google's pretty big, and I'm a DeepMind. So there was a DeepMind work in the past where they used this for Google data center cooling. They were able to reduce that energy percentage by a certain amount. I primarily worked on the research side of things, so it's hard for me to actually see how it's applied. But as you can imagine, we open sourced the papers. I would be happy to see how other people would be open to using the technology using different areas. I think there's some research in the motor work, which I shared. So, in motor control. But typically any industrial system that shares the same characteristics, right? Like you have a simulation, you have noise, you have different tasks, could be integrated into a task suite like this for some sort of control or optimization task.
So what you're saying is in your space, you're creating the tools that then can be used out in the practical world. So that's what you're talking about now.
Yeah. So in our paper, we basically we haven't kind of detailed the paper in quite depth on how others could develop a simulation like ours.
Right.
And we put a lot of code snippets as well, along with the high-level system design, so others could also use this for their own industrial purposes.
Cool.
So in this paper, we kind of created that sort of simulation framework.
Awesome. Thank you.
Yeah, of course. Thanks for the question.
I have a similar question. This might be very obvious, but maybe it's just not clicking for me. So I understand this to be a simulation, but if it were to, I know you don't do application, but if it were to be applied, would it require any kind of different components to be added into the buildings that we put this in? Will you have to have more technology in there? Okay.
Yeah, so basically, so there was, I can refer to a public blog, by DeepMind. So there was some work, thanks Peter. There was some work on applying this to Google data centers. And so, I joined in the project. So that is there. But typically, if you talk more generally, there's something called sim to real. So when you have these sort of simulation frameworks here, you want to build an adapter so that if an agent works well in the simulation, can you maybe do a dry run in a real world facility and then see how well it performs on that. It's sort of A/B testing it. But basically, sim to real, in technically, it's quite a hard challenge. A lot of researchers have worked on it, and there's obviously a lot of work to get a very good high fidelity simulation of something like this. So there would be a gap. For example, you won't get the exact same values you get in the simulation to a real world facility unless you tune it like really, really, really well, right? So a gap still exists, but the goal with something like this is that you're able to use it to benchmark different agents. So the exact performance number doesn't matter as much versus like, can you answer questions on like, is agent A or agent B better on the real world by just comparing them in the simulation framework, right?
Okay.
So those are questions that could be very easily addressed in simulations, and then you have a sim to real adapter, and then you could deploy them in real world environments.
So you're saying that you wouldn't necessarily need to input these like technologies into each building, but rather you could learn lessons from like what the algorithm learns and apply that, like tell people how to run their cooling systems better.
Yeah. I mean, I guess you could do the other two. Like I've seen public research work. Let's say I've seen I've seen public research where people have applied this in their buildings, and then they have sensors, and then the sensors collect data, and then it goes to an agent. An agent makes a reasonable inference from data and says, okay, I want you to turn the chiller on or off, and it goes back to the actual control of the building. So I think I can find those papers. There are real world control applications for this.
Thank you. Yeah, that's really interesting.
Yeah. I think the last part of your question was like, what technology do we need to kind of enable it? Sorry, I missed this. So I think like having a very good sensor framework, like having the field of IoT, it's seen a lot of growth in the last few decades. But yeah, basically like having like sensors that can accurately give good data to like an agent to learn from, being able to have the sort of real time pipeline. Because for example, if an agent takes like 10 minutes to create a recommendation, and then there's a latency in transmission of that to the environment for the real world facility, another 10 minutes, there's a round trip of 20. And by that time, it'd be too late, right? Like to actually do recommendations. So you need to have a, nice infrastructure set up to support this near real time recommendations.
Well, okay, cool. Thank you. Dan or Mariana, do you have any questions on this research or just about DeepMind in general, maybe?
Yeah, technical question, Praneet. Hey, I know we spoke before on something.
Yeah.
So how exactly are the hard physical constraints being enforced here? Because I've seen different ways of tackling this depending on areas of research, right? So for physics, they get a PDE representing the dynamics that the equation, that the underlying network should try and learn and enforce it as a regularization. Other places like D3C, which you might have heard of, basically tries to do a combination of like generate an answer regardless if it meets the constraint of the optimization, and then just project it back into the feasible set or do something along those lines. So I'm curious in this case, how it's expected.
Yeah, that's a great question. Yeah, I kind of skimmed over that. So that's an interesting aspect. So I guess we designed the environment in the way that it's up to the user. So we have, if you read the paper, we have this thing called soft constraints and hard constraints. So soft constraints are basically something that it's okay if the agent violates it a few times, like once, but if it violates it more than a certain threshold, or like a rolling average, in that case, we give the agent a large negative penalty, or which there are different ways of handling it. You can either terminate a given simulated episode, you can give it a large penalty, but basically you can penalize it, right? I assume in a real building, you would just want to like close down agent control and then, manually take over or something. But in the simulation, you have flexibility on handling it however you want. So let's say I want a temperature at 72 Fahrenheit, and the agent like somehow sets the chiller temperature in such a way that it goes to 70 to 74. I won't mind too much if it's out for like 30 seconds or a few minutes, but if it's more than 20 minutes, the temperature is very high, I might get annoyed, right? So that's a soft constraint violated. We might also have hard constraints. So let's say if you keep talking about temperature, let's say that the agent suddenly shoots up the building temperature to 95 degrees, right? I'm going to immediately complain. Doesn't matter if it's, for like 30 seconds or not, it's really, really hot now, right? So a single violation of a hard constraint means that the simulation is terminated, and, the agent should then learn to infer that not to do that, right? Other things too, like, we care about maintaining a regular flow rate of water to the pipes. You don't want the water pressure to be too low or too high. So you have constraints on the low upper bound and lower point of distribution differential pressure. And similar for other things like, flow rate and temperatures across the chilled water plant system. the last part of your question, I guess, was like on how agents handle it. So like, I guess usually on how it sees the rewards. So, if it sees a large negative penalty, it should be able to infer that it did something which it should not have, and then explore other part of the action space so that it kind of bypasses that.
Right. So then basically it all depends on how the external environment is essentially stipulated to be able to sort of embody those constraints into the environment.
Yeah, exactly. And each of these are like different research challenges, right? Like, I mean, it's still, there's no like, or at least I'm not aware of any set way of doing it. Like, you can choose to like give it explicit constraints and terminate episodes, or you can choose to like just give it a large negative penalty and hope that the agent learns along the way.
Right. Thank you. And then the last question I had was like, so given that this sort of external environment kind of determines a lot of things, right? And given that the supposed user uses a suite, then in some cases where, let's say, never before happened tail risk events occur, it can really sort of catch the system or catch the agent off guard, right? So as a specific example, like in some of my previous work when we were dealing with MIT's E1 supercluster, right? It's like in the middle of Wellesley, Massachusetts.
Yeah.
And while it's able to operate within a wide range of temperatures, we started seeing like large, really high temperatures, right? To the point where someone was like, well, one day if we reach 115 to 120 degrees Celsius, some of the stuff near the external power station dedicated specifically to this cluster might actually start melting, like the metal grids on it might start melting.
Yeah.
And so I'm curious in this case, like, are there early warning signs in the sense that, you have a deterministic state action space that's already specified in the environment? Are there ways for users in the suite to have like early signs saying like, oh, these things are moving in the wrong direction, or these things are becoming non-stationary? Like, is there some sense of that built in?
Yeah. So that's a great question. Multiple ways to answer. The first thing is like safety constraints. Let's say things get too hot, then at that level, it'll trigger an alarm. So you have like, let's say the temperature. If I go back to my plot, there was a temperature on, what the maximum temperature the building can get, right? If it goes over that, it kind of rings that alarm, and then it alerts the simulation, the episode to shut down. In terms of simulating these, I think that's something which was like the crux of a motivation for this. There's a term in reinforcement learning literature called domain randomization, where you're able to take different combinations of like external weather temperatures, building load, and tasks so that you can simulate a very hot day around Boston as well, which you might not see much in practice, and then see how well the agent generalizes to it, right? So by like giving it as many of these distinct scenarios as possible, the hope is it's able to learn a more generalizable policy versus what you would see by just doing online interactions, and that's why we need a simulation, because then we can kind of set up these hypothetical scenarios without having the agent to see it for the first time in a real world facility.
Cool. Thank you.